yourself a beverage, a hop if you wanna just bounce to my leverage. The evidence, as they say, is in the pudding. So
Go.
Oh, hey, didn't see you there. This is Andrew Keating, and today I'm going to talk to you about a famous momentum scientist named Sir Isaac Newton. He's said to be born on the 25th of December, 1642, and although his death date is skeptical, it is said that he died on the 20th of March, 1726. And the experiment that he's most famous for, or the invention, is Newton's cradle. The discovery date is unknown, but it demonstrates 5 balls that show that when it acted upon, it transfers energy and momentum to the same side. I'm going to demonstrate this. As you can see, momentum transfers to the 3 balls in the middle and delivers at the end ball. The significance of this experiment is that it demonstrates his 3rd law, which states that for every action there is an equal and opposite reaction. And this helps scientists later on. Period.
Oh. Hey there, I'm Will Simmons. Today I'll be talking about aspects of momentum. So first, we got 2 laws. One, the law of inertia, which says an object at rest tends to stay in rest, which kind of works the same, however an object in motion tends to stay in motion. So we got another law of conservation of momentum. With this, we see that there's a vector quantity. We see that moving objects will have kinetic energy, and that objects that collide at the same rate of speed causes momentum to cancel out. Because of this, we have impulse, which impulse is the force multiplied by the time. So then we have 3 types of collisions. 1, perfectly inelastic. This states that 2 objects collide but become stuck together. We have inelastic collisions, where momentum is conserved. This is where 2 objects collide and bounce off each other. And the last one, elastic, which is basically the same as inelastic, but energy is conserved. So these are 4 aspects of momentum.
Whoa, earthquake!
Oh, hey, good to see you there. Today we're going to be talking about how to solve a problem of momentum in physics. Now, the great Andrew Keating is going to read out the problem aloud.
1,250 kilogram sports car starts from rest and accelerates at a constant rate of 4 meters per second for 15 seconds. However, the street is a one-way street, and the car collides with a stationary 2,000 kilogram SUV and they stick together. What is the coefficient of kinetic friction if a car takes 15 meters to fully stop?
Now, keep in mind a few things before you start the problem. 1, read it over fully like Andrew did so nicely. Then, read it over again and list your variables. Once you do that, you're going to draw a picture of the scenery, like the car driving, colliding, and then sliding, and write down all the information. And after that, you're going to write either an FBD or a nice bar chart like we have here. Now, I'm going to go into the problem. Now, first thing I did was drew a picture. Drew the car, 1,250 kilograms,
So, first things first, let's
driving along for 15 seconds at 4 meters per second.
At point B, which is
And then
at the
it
bottom
glides
of
with
the
a
first,
stationary 2,000 kilogram car,
the first drop.
which then they both stick together and slide 15 meters.
1.5.
So number 2,
Right? Okay.
we had to find out the final velocity
1.5 times. Right?
once of the collision. So you did VF equals VI plus A times delta T. So 4 times 15 plus 0 is 60. So that's 60. Then you're going into your M at mass A, mass B. So that's car 1, car 2. 1 is A, 2 is B. What you get is 75,000 plus 3,250. You divide, you get final velocity of the collision, or this is final velocity of the car, final velocity of the collision, 23.08.
Because you've made some
Then you go into the bar chart. This is where it gets fun. KE is up because the car is moving. PG is 0 because it's flat, there's no incline or decline. Work is negative because there's friction. And at the end, both cars are stopped So the K is 0, and they're both on the ground still, so it's PEG 0.
Your little stick.
Now, what we're going to do is go into
2.5.
the bar chart work. 1/2 mv squared minus mu mg delta d equals 0. 1/2
is the force applied.
squared mu mass times gravity, or mass times
That means
distance.
the normal force is
Mass,
squared
gravity,
times
distance.
gravity.
You got this?
Down, normal force
mu
is up,
equals
normal
1.8.
acceleration is 1.5.
And that's how you do a beautiful problem
Acceleration should be
in physics.
14.
Hey there, Rob Ripsky.
Will Simmons.
And this is Real Life Connections.
Saying to me that this is positive.
Now, our first real life connection is in airbags in the car. Our second is hitting a baseball. Third is cars driving. Fourth is cars hitting a wall. Fifth is water balloon. And sixth is fireworks. Some activities we do are driving, baseball, running, fireworks, shooting out fireworks, water balloon tosses, throwing a water balloon on the ground and it splatters, bouncy balls. Hey there, Rob Ripsky.
Will Simmons.
And this is Real Life Connections.
Saying to me that this is positive.
Now, our first real life connection is in airbags in the car. Our second is hitting a baseball. Third is cars driving. Fourth is cars hitting a wall. Fifth is water balloon. And sixth is fireworks. Some activities we do are driving, baseball, running, fireworks, shooting out fireworks, water balloon tosses, throwing a water balloon on the ground and it splatters, bouncy balls.
Okay, here's our first example of a momentum problem. A 0.62 kilogram volleyball flies towards you at 4.3 meters per second. You hit it back from a height of 1.5 meters, and then you hit it with an average force of 400 newtons, and your hands are in contact for 0.03 seconds. What is the ball's velocity after you hit it, and how far does the ball travel? First, you start off with impulse that equals the mass velocity minus the mass of the velocity initial. And since impulse equals velocity delta t, force delta t equals the mass final minus mass and velocity initial. So here we plug in the numbers, and 400 is going to be negative since it's coming back at you, going left. And then the time that you hit it is 0.3 seconds. Then the mass is 0.62, and the velocity final is what you're trying to figure out. So you subtract that by the mass times the velocity initial. Then through simple equation math, you find the velocity final equals negative 15.1 meters per second, which makes sense because it's coming towards the left. Then you put it into the XY chart and you use MathRep 4 to figure out the time. And here we fill in the distance of the y, which would be the height, and you put in the acceleration, which is negative 9.8 because gravity is acting upon the object. And after you find that time equals 0.55 seconds, and you multiply time over when you put it in MathRep 1, and negative 15.1 times 0.55 gives you the x distance at 8.28 meters. Go.
Alright, so in this problem, a 5 kilogram ball is being thrown with a velocity of 15 meters per second at a wall. And then, after that, it hits the wall and it bounces back. We have to find the impulse and the force. So impulse problem, there's many different formulas for impulse, but for this problem, you use mass final minus mass velocity final minus mass velocity initial. So the mass final, or in the velocity final, negative 15, initial 15, you get negative 75 minus 75, which is negative 115 meters times meter per second. That's the impulse. To find the force, you do I equals F delta T, and you have I of delta T because it takes 0.10 seconds. It stays on the wall for 0.10 seconds. So you take 0.10 and divide it by negative 150, which you get negative 1,500 for force in newtons.
We had a 2,000 kilogram truck skids 10 meters down a 30-degree hill. The coefficient of friction between the truck's tires and the ground is 0.3. At the bottom of the hill, the truck crashes into a 600 kilogram smart car that was driving 10 meters towards the hill. They stick together and slide. What is the velocity of the two right after the collision? So first, I drew my picture. So we got both cars, the angle, how much they weigh. So first we start with the mass of the first one times the initial velocity of both of them equals the mass of the first one again times the final velocity plus the mass of the second one times that final velocity. So you plug in and we get 2,000 x plus 600 times 10 equals 2,000 VF plus 600 VF. And since they're sticking together, these VFs are going to be the same. So we're going to combine them to get 26,000 VF, 2,600 VF. And since we don't have, since we have two variables, we go to the bar chart. So we get that it starts out not moving, and then it's up on the ground with negative work, and then it ends moving, but it's on the ground. So we get mgh minus mu fn delta d equals 1/2 mv squared. So we plug that in, we get 2,000 times 9.8 times 5 minus 0.3 times 2,000 times 9.8 times cosine 30 times 10 equals 1/2 2,000 v squared. And when we solve for v, we get that equals 6.86 meters per second. And then we plug that in back into this top equation, and then we get 2,000 times 6.86 minus 600 or minus 6,000 equals 2,600, and then you get that the final velocity of them stuck together is 2.97 meters per second.